So when it says use the Fourier method, this is something we haven't broken down step by step just yet. Even if we have done all of the steps individually in isolation, this is where they all come together to serve a unifying purpose. So what is the Fourier method? Well, the Fourier method starts by finding the general solution to the boundary value problem itself. So that's this data here in the first 3 lines. Consists of the partial differential equation along with its boundary conditions. So find the general solution of the boundary value problem. And that one uber sort of step here usually includes several smaller steps. This is where you can reference homework 3. In fact, you can note for note reference homework 3 problem number 1 because that problem dealt specifically with the equation for heat transfer that we're using here. It also dealt specifically with the kinds of boundary conditions that we're using here. It's actually the second part of homework 3 question number 1 dealt with what happens when the boundary conditions involve the derivative instead of involving the value of the function. And so the sort of the steps that are in here, and you don't necessarily have to show me all of them. Show me as many as will help you to make your case. But use separation of variables. To write your solution u of x and t as a product of capital X, which is a function of x, times capital T, which is a function of little t. And then plug that into the partial differential equation. And that will allow you to separate it into a pair of ordinary differential equations. And I think it's fair for me to say, because I've already posted the solutions to homework 3, what those ODEs end up looking like. X double prime plus lambda x equals 0, and t prime plus lambda kt equals 0. You solve each one of those ordinary differential equations, and because we don't use ordinary differential equations as a prerequisite, this is a place where I can just give you, or you can feel free to look up. You won't have any questions on the exam which will require you to solve new ordinary differential equations. So every ODE that you would need to solve on the exam is one of these two, essentially. So I'm not going to be pulling any new ones out of a hat for you. But the general solution for the capital X function is, let's call it capital A sub, how do I want to call this? Capital A1 times the cosine of x squared root of lambda plus capital B1 times the sine of x times the square root of lambda. And the time dependence, capital T of t. This, because it's a first order or ordinary differential equation, you could solve it using Calc 2 methods just by separating those variables and getting, let's call it capital C1 times e to the minus k t lambda, minus k lambda t. And so the general solution for this ordinary differential equation looks like a product of these two types of functions. And so you can then use the principle of superposition to come up with the general solution looking like a big old sum of these products. But then we also have to impose the boundary conditions. I suppose before I even go any further, before I add these together and try to superpose them, I should rewrite this as something like C1 times e to the minus, actually, sorry, let me pull the exponentials out to the front. E to the minus lambda kt. And then I'll put my constants on the inside here. Let's say A1 times cosine x root lambda plus B1 times sine x root lambda. And then you'll need to use the boundary conditions to do two things. And this is, I guess, step C here. impose the boundary conditions, BCs, these things right here. And those should tell us something about the constants, A1 and B1, that we're allowed to have here. And they should also, in some fashion, tell us about lambda. So the boundary conditions really hold a lot of power here. They're going to tell us, for example, whether we need either A1 or B1 here to be 0. In other words, if we need cosines of x squared lambda, or if we need sines of x squared lambda at all in our separated solution. The boundary condition should also tell us whether lambda gets to be just anything at once, or whether it has to take on specific values. For example, integer multiples of pi, that sort of thing. So imposing the boundary condition should straighten that out and give us a particular form for these separated solutions that we can then glue together into the general solution of the boundary value problem. So that really does track along with all the work that goes into homework 3, question number 1. And then what happens from there, step 2 in the Fourier method, is how we can then fit that information, that general solution, to our initial data. And our initial data is this function u of x and 0. In this example, it's a step function. It's a 100 from 0 to 2 and 0 from 2 to 4. And so step 2 is just to match u of x 0 with this function. Using Fourier coefficients. So for example, since I don't want to do exactly the problem that I've assigned you, I'm going to just change this a little bit. I'm going to change the boundary conditions so that instead of being the derivative with respect to x at 0 and 4, let's just make it the value of the function at 0 and 4 are equal to 0. With all that information taken together, we can show, as you did, again, on homework 3, question 1, that information taken together would have shown us that the general form of the solution is u of x and t is the sum of some coefficient, bn, times e to the minus n squared pi squared kt over L squared, and L is 4 here, so that ends up being 16, times the sine of n pi over 4 times x. So the solution of the boundary value problem would give us a series that looks like this, where the time dependence came from the solution of our t of t equation, the space dependence came from the solution of the x of x equation, and those combined together with the boundary conditions explain the disappearance of the cosine and the quantization of the lambdas to be n squared pi squared over 16. Okay. So all of that went into the general solution of the boundary value problem. And it's then, at step 2, that we say, well, what if t is equal to 0 in this function? Well, if t is equal to 0, our space dependence becomes a big fat 1. And so we just end up with bn times the sine of n pi over 4 times x from 1 to infinity. But then that is supposed to equal the piecewise function that we've been given here. And the way that we have to make that equality happen is to set the b sub n's equal to the Fourier coefficients of that function. And in this example, because our building blocks are sines, bn is going to be, I'm just going to write it in English first, Fourier sine coefficients of this function, the piecewise function which is 100 from 0 to 2 and which is 0 from 2 to 4. And according to what we know about Fourier sine coefficients, that's going to be 2 over L times the integral from 0 to L of f of x, where f of x again is that piecewise function, times the sine of n pi over 4 times x with respect to x. And so then you have an integration problem to do. You crank out this integral, you get some expression that still has n's in it because the different coefficients are probably going to have different values. And then those coefficients are what you stuff into the b sub n's to give us the specific form of the overall solution.